Elixir School. Comprehensions. List comprehensions are syntactic sugar for looping through enumerables in Elixir. In this lesson, we'll look at how to use comprehensions for iteration and generation. Basics. Oftentimes, comprehensions can be used to produce more concise statements for enum and stream iteration. Let's start by looking at a simple comprehension and then break it down. List 1, 2, 3, 4, 5 for x. List do x times x. The first thing we notice is the use of for and a generator. What is a generator? Generators are the x left arrow expressions found in list comprehensions. They're responsible for generating the next value. Lucky for us, comprehensions aren't limited to lists. In fact, they'll work on any enumerable. Whoa, dude. The fuck? Like many other things in Elixir, generators rely on pattern matching to compare their input set to the left side variable. In the event a match is not found, the value is ignored. It's really useful. It's possible to use multiple generators, much like nested loops. To better illustrate the looping that is occurring, let's use IO puts to display the two generated values. List comprehensions are syntactic sugar and should be used only when appropriate. Filters. You can think of filters as a sort of guard for comprehensions. When a filtered value returns false or nil, it is excluded from the final result or the final list. Let's loop over a range and only worry about even numbers. We'll use the isEven1 function from the integer module to check if a value is even or not. Like generators, we can use multiple filters. Let's expand our range and then filter only for values that are both even and evenly divisible by 3. Using into. What if we want to produce something other than a list? Given the into option, we can do just that. As a general rule of thumb, into accepts any structure that implements the collectible protocol. Using into, let's create a map from a keyword list. Reduce. Since binaries are collectibles, we can use list comprehensions and the into to create strings. That's it. List comprehensions are an easy way to iterate through collections in a concise manner. Strings. strings, char lists, graphemes, graphemes, and code points. Strings. Elixir strings are nothing but a sequence of bytes. Let's look at an example. By concatenating the string with the byte 0, IEX displays the string as binary because it is not a valid string anymore. This trick can help us view the underlying bytes of any string. Note the double pointy bracket syntax. Using the double pointy bracket syntax, we are saying to the compiler that the elements inside those symbols are bytes. Char lists. Internally, Elixir strings are represented with a sequence of bytes rather than an array of characters. Elixir also has a char list type, character list. Elixir strings are enclosed with double quotes, while char lists are enclosed with single quotes. What's the difference? Each value in a char list is the Unicode code point of a character, whereas in a binary, the code points are encoded as UTF-8. Let's dig in. .322 is the Unicode code point for /L, but it is encoded in UTF-8 as the 2 bytes 197 and 130. You can get a character's code point using the question mark. This allows you to use the notation $Z rather than Z for a symbol. When programming in Elixir, we usually use strings, not char lists. The char list support is mainly included because it is required for some Erlang modules. For further information, see official Getting Started guide. Graphemes and code points. Code points are just simple Unicode characters which are represented by one or more bytes, depending on the UTF-8 encoding. Characters outside of the US ASCII character set will always encode as more than one byte. For example, Latin characters with a tilde or accents are typically encoded as 2 bytes. Characters from Asian languages are often encoded as 3 or 4 bytes. Graphemes consist of multiple code points that are rendered as a single character. The string module already provides 2 functions to obtain them, graphemes1 and codepoints1. Let's look at an example. String codepoints. Oh, hey, thanks. Is don't, but platformatic. String functions. Increase that. Thanks for the feedback. String functions. Let's review some of the most important and useful functions of the string module. This lesson will only cover a subset of the available functions. To see a complete list of functions, visit the official string docs. Length 1 returns the number of graphemes in the string. Replace 3 returns a new string replacing a current pattern in the string with a new replacement string. Duplicate 2 returns a new string repeated n times. Split 2 returns a list of strings split by a pattern. Exercises. Let's walk through a simple exercise to demonstrate we are ready to go with strings. anagrams. A and B are considered anagrams if there is a way to rearrange A or B, making them equal. For example, A equals super, B equals Perus. If we rearrange the characters on string A, we can get string B and vice versa. So, how can we check if two strings are anagrams in Elixir? The easiest solution is to just sort the graphemes of each string alphabetically and then check if they are both equal. Let's try that. Let's first give a watch to anagrams 2. We are checking whether the parameters we are receiving are binaries or not. That's the way we check if a parameter is a string in Elixir. After that, we are calling a function that orders the string alphabetically. It first converts the string to lowercase and then uses string graphemes1 to get a list of graphemes in the string. Finally, it pipes that list into enum sort. Pretty straight, right? Let's check the output on IEX. As you can see, the last call to anagrams caused a function clause error. This error is telling us that there is no function in our module that meets the pattern of receiving two non-binary arguments. And that's exactly what we want, to just receive two strings and nothing more. Date and time. Working with time in Elixir. Elixir has some modules which work with time, though it needs to be noted that this functionality is limited to working with the UTC time zone. Let's start with getting the current time. Time.utc now. Note that we have a sigil which can be used to create a time struct as well. You can learn more about sigils in the lesson about sigils. It is easy to access parts of this struct. .hour, .minute, .day, but there's no day in this. So let's look at date. But there's a catch. As you may have noticed, this struct only contains time within a day. No day, month, year data is present. Date. Contrary to time and date, struct has info about the current date, with any info about current time, without any info about current time. Date.utc today, but it has some useful functions to work with dates. Day of week, leap year. Day of week 1 calculates which day of the week would be the given date. In this case, it's Saturday. Leap year checks whether this is a leap year. Other functions can be found in doc. Naive date time. There are two kinds of structs which contain both date and time at once in Elixir. First of two is naive date time. Its disadvantage is lack of time zone support. Naive date time, UTC now. But it has both the current time and date, so you can play with adding time, for example. Date time. The second one, as you may have guessed from the title of this section, is date time. It does not have the limitations noted previously. It has time and date and supports time zones. But note about time zones from the official doc. You will notice this module only contains conversion. You will notice this module only contains conversion functions as well as functions that work with UTC, that work on UTC. This is because a proper date-time implementation requires a time zone database, which currently is not provided as part of Elixir. Also note that you can create a date-time instance from the naive datetime just by providing the time zone. Datetime from naive date, then time zone. This is it. If you want to work with other advanced functions, you may consider looking further into docs for time, date, and datetime. You should also consider Timex and Calendar, which are powerful libraries to work with time in Elixir. Custom mix tasks. Creating custom mix tasks for your Elixir projects. Introduction. It's not uncommon to want to extend your Elixir application functionality by adding custom mix tasks. Before we learn about how to create specific mix tasks for our projects, let's look at one that already exists. Mix Phoenix New My Phoenix App. As we can see from the shell command above, the Phoenix framework has a custom mix task to generate a new project. But what if we could create something similar for our project? Well, the great news is we can, and Elixir makes this easy for us to do. Setup. Let's set up a very basic mix application. Mix new hello. Now in our lib hello file that mix generated for us, let's create a simple function that will output hello world. Hello say. Let's create our custom mix task. Create a new directory and file hello lib mix tasks hello. Within this file, let's insert these 7 lines of Elixir. Def module mix.tasks.hello, use mix task, and run. Notice how we start the def module statement with mix tasks and name what we want to call from the command line and the name we want to call from the command line. On the second line, we introduce use mix tasks, which brings the mix task behavior into the namespace. We then declare a run function, which ignores any arguments for now. Within this function, we call our hello module and the say function. Mix tasks in action. Let's check out our mix task. As long as we are in the directory, it should work. From the command line, run mix hello. Mix is quite friendly by default. It knows that everyone can make a spelling error now and then, so it uses a technique called fuzzy string matching to make recommendations. Mix hell. Did you also notice we introduced a new module attribute, shortdoc? This comes in handy when shipping our application, such as when a user runs the mix help command from the terminal. Note, our code must be compiled before new tasks will appear in the mix help output. We can do this either by running mix compile directly or by running our task like we did with mix hello, which will trigger the compilation for us. IEX helpers. As you begin to work in Elixir, IEX is your best friend. It is a REPL, but it has many advanced features that can make life easier when exploring new code or developing your own work as you go. It'd be nice if it had an exit function. It's cool though, right? Control C and then A. That's how I've been exiting everything. There are a slew of built-in helpers that we'll go over in this lesson. Autocomplete. When working in the shell, you might often find yourself using a new module that you're unfamiliar with. To understand some of what is available to you, the autocomplete functionality is wonderful. Simply type a module name followed by period and press tab. And now we know the functions we have and their arity. .iex.exs file. Every time IEX starts, it will look for a .iex.exs configuration file. If it's not present in the current directory, then the user's home directory, didn't know that, will be used as a fallback. Configuration options and code defined within this file will be available to us when the IEX shell starts up. For instance, if we want some helper functions available to us in IEX, we can open up .iex.exs and make some changes. Let's start by adding a module with a few helper functions. What's this? Now when we run IEX, we'll have the IEX helpers module available to us from the start. Open up IEX and let's try out our new helpers. What's this? String. Binary. What's this? Unknown. What's this? An atom. As we can see, we don't need to do anything special to require or import our helpers. IEX handles that for us. H. H is one of the most useful tools in our Elixir shell. H is one of the most useful tools our Elixir shell gives us. Due to the language's fantastic first-class support for documentation, the docs for any code can be reached using this helper. To see it in action is simple. H enum. H any module or function. And now we can even combine this with the autocomplete features of our shell. Imagine we are exploring map for the first time. H map in map.tab. As we can see, we are not only able to find what functions were available as part of the module, but we were able to access individual function docs, many of which include example usage. Let's put some of our newfound knowledge to use by employing H to learn a bit about the I helper. I prints information about the given data type. Whoa. Wow. That's neat. Now we have a bunch of information about map including where its source is stored and the modules it references. This is quite useful when exploring custom foreign data types and new functions. The individual headings can be dense, but at a high level, we can gather some relevant information. It's an Atom data type, where the source code is, the version and compile options, a general description, how to access it, what other modules it references. This gives us a lot to work with and is better than going in blind. R. If we want to recompile a particular module, we can use the R helper. Let's say we've changed some code and want to run a new function we've added. To do that, we need to save our changes and recompile with R. T. The T helper tells us about types available in a given module. T module. And now we know that map defines the key and value types in its implementation. If we go and look at the source of map, this is a simple example stating that keys and values per the implementation can be any type, but is useful to know. By leveraging all these built-in niceties, we can easily explore the code and learn more about how things work. IEX is a very powerful and robust tool that empowers developers. With these tools in our toolbox, exploring and building can be even more fun. Erlang interoperability. One of the added benefits to building on top of the Erlang VM beam is the plethora of existing libraries available to us. Interoperability allows us to leverage those libraries and the Erlang standard lib from our Elixir code. In this lesson, we'll look at how to access functionality in the standard lib along with third-party Erlang packages. Standard library. Erlang's extensive standard library can be accessed from any Elixir code in our application. Erlang modules are represented by lowercase atoms such as OS and timer. Let's use timer.tc to time execution of a given function. Well, that's cool. Oh, man. For a complete list of modules available, see the Erlang reference manual. Erlang packages. In a prior lesson, we covered mix and managing our dependencies. Including Erlang libraries works the same way. In the event that the Erlang library has not been pushed to Hex, you can refer to the Git repository instead. Ping, GitHub, use, ping. Now we can access our Erlang library. Whoa. Surprised they're not namespaced. Notable differences. Now that we know how to use Erlang, we should cover some of the gotchas that come with Erlang interoperability. Atoms. Erlang atoms look much like their Elixir counterparts without the colon. They are represented by lowercase strings and underscores. Oh, they are namespace. Well, Huh. Strings. In Elixir, when we talk about strings, we mean UTF-8 encoded binaries. In Erlang, strings still use double quotes but refer to char lists. Oh, wait, that feels strange. It is important to note that many older Erlang libraries may not support binaries, so we need to convert Elixir strings to char lists. Thankfully, this is easy to accomplish with the toCharList function. You know what else I wish? That the IO puts, that I didn't have to, well, that it had a guard clause that says, hey, if it's an array or map or something, that it adds the as char list true, or yeah, by default. String words, variables, Elixir, Erlang. Man, this dot, that is weird. That's it. Leveraging Erlang from our Elixir applications is easy and effectively doubles the number of libraries available to us. Error handling. Although more common to return the error reason tuple, Elixir supports exceptions, and in this lesson, we'll look at how to handle errors and the different mechanisms available to us. In general, the convention in Elixir is to create a function, example 1, which returns OK result and error reason, and a separate function, example 1, pound, or bang, that returns the unwrapped result or raises an error. This lesson will focus on interacting with the latter. Before we can handle errors, we need to create them, and the simplest way to do that is with raise1. Raise, oh no, runtime error. If we want to specify the type and message, we need to use raise2. Raise, type of error, and keyword list of message. The argument value is invalid. When we know an error may occur, we can handle it using the try, rescue, and pattern matching. It's possible to match multiple errors in a single rescue. After. It's like a finally. Or ensure. At times, it may be necessary to perform some action after our try rescue regardless of error. For this, we have try after. If you're familiar with Ruby, this is akin to begin, rescue, ensure, or in Java, try, catch, finally. This is most commonly used with files or connections that should be closed. New errors. While Elixir includes a number of built-in error types, like like runtime error, we maintain the ability to create our own if we need something specific. Creating a new error is easy with def exception 1 macro, which conveniently accepts the message option to set a default error message. Let's take our new error for a spin. Raise example error. Throws. Another mechanism for working with errors in Elixir is throw and catch. In practice, these occur very infrequently in newer Elixir code, but it's important to know and understand them nonetheless. Throw1 function gives us the ability to exit execution with a specific value we can catch and use. As mentioned, throws and catches are quite uncommon and typically exist as stopgaps when libraries fail to provide adequate APIs. Exiting. The final error mechanism Elixir provides us with is exit. Exit signals occur whenever a process dies and are an important part of the fault tolerance of Elixir. We can explicitly exit, to explicitly exit, we can use exit 1. Oh no. With reason, oh no. While it is possible to catch an exit with try catch, doing so is extremely rare. In almost all cases, it is advantageous to let the supervisor handle the process exit. Executables. To build executables in Elixir, we will be using eScript. eScript provides an executable that can be run on any system with Erlang installed. Cool. Getting started. To create an executable with eScript, there are only a few things we need to do. Implement a main function and update our mix file. We'll start by creating a module to serve as the entry point to our executable. This is where we'll implement main1. Next, we need to update our mix file to include the eScript option. For our project, along with specifying our main module. Parsing args. With our application set up, we can move on to parsing the command line arguments. To do this, we'll use Elixir's option parser, parse2, with the switches option to indicate that our flag is Boolean. Switches, uppercase, Boolean. Response. Building. Once we've finished configuring our application to use eScript, building our executable is a breeze with mix. Mix eScript.build. Let's take it for a spin. Example app -- uppercase. Hello. Hello. And without the uppercase option, it just prints what it is. That's it. We've built our first executable in Elixir using eScript. Concurrency. One of the selling points of Elixir is its support for concurrency. Thanks to the Erlang VM beam, concurrency in Elixir is easier than expected. Alrighty. The concurrency model relies on actors, a contained process that communicates with other processes through message passing. In this lesson, we'll look at the concurrency modules that ship with Elixir. In the following chapter, we'll cover the OTP behaviors and implement them. Processes. Processes in the Erlang VM are lightweight and run across all CPUs. While they may seem like native threads, they're simpler, and it's not uncommon to have thousands of concurrent processes in an Elixir application. The easiest way to create a new process is spawn, which takes either an anonymous or named function. When we create a new process, it returns a process identifier, or PID, to uniquely identify it within our application. To start, we'll create a module and define a function we'd like to run. To evaluate the function asynchronously, use spawn3. Spawn, example, add, and then args. Message passing. To communicate, processes rely on message passing. There are two main components to this: send to and receive. The send to function allows us to send messages to PIDs. To listen, we use receive to match messages. If no match is found, the execution continues uninterrupted. No blocking or no. Does it queue up? PID, spawn, listen, send, PID. If no match is found, the execution continues uninterrupted. So if nothing is found here, continues. Still listening. You may notice that the listen zero function is recursive. This allows our process to handle multiple messages. Without recursion, our process would exit after handling the first message. Process linking. One problem with spawn is knowing when a process crashes. For that, we need to link our processes using spawn link. Two linked processes will receive exit notifications from one another. Explode, do, exit, kaboom. Spawn, explode, spawn link. It's linked to the current process. Sometimes we don't want our linked process to crash the current one. For that, we need to trap the exits using process flag 2. It uses Erlang's process flag 2 function for the trap exit flag. When trapping exits, trap exit is set to true. Exit signals will be received as a tuple message. Exit from PID reason. Receive. Exit from PID reason. Process monitoring. What if we don't want to link two processes but still be kept informed? For that, we can use process monitoring with spawn monitor. When we monitor a process, we get a message if the process crashes without our current process crashing or needing to explicitly trap exits. Down. Ref and process. I wonder what ref is. A reference to the process? But it's agents. Agents are an abstraction around background processes maintaining state. We can access them through other processes within our application and node. The state of our agent is set to our function's return value. The state of our agent is set to our function's return value. Agent update. 1, 2, 3, 4, 5. Agent get agent. When we name an agent, we can refer to it by that instead of its PID. Tasks. Tasks provide a way to execute a function in the background and retrieve its return value later. They can be particularly useful when handling expensive operations without blocking the application execution. Oh. Is there a nice dashboard for managing those to see which ones fail in a Phoenix app? Because that would be neat. Erlang. Task async, example, double, args. Task await. OTP concurrency. We've looked at Elixir Elixir abstractions for concurrency, but sometimes we need greater control, and for that we turn to the OTP behaviors that Elixir is built on. In this lesson, we'll focus on the biggest piece, gen servers. Gen server. An OTP server is a module with a gen server behavior that implements a set of callbacks. At its most basic level, a gen server is a single process which run loop that handles one message per iteration, passing along an updated state. To demonstrate the gen server API, we'll implement a basic queue to store and receive values. To begin our gen server, we need to start it and handle the initialization. In most cases, we'll want to link processes, so we use gen server start link. We pass in the gen server module we're starting, initial arguments, and a set of gen server options. The arguments will be passed to gen server init, which sets the initial state through its return value. In our example, the arguments will be our initial state. Synchronous functions. It's often necessary to interact with gen servers in a synchronous way, calling a function and waiting for its response. To handle synchronous requests, we need to implement the gen server handle call 3 callback, which takes the request, the caller's PID, and the existing state. It is expected to reply by returning a tuple. With pattern matching, we can define callbacks for many different requests and states. A complete list of accepted values can be found in genserver handle call 3 docs. To demonstrate synchronous requests, let's add the ability to display our current queue and remove a value. Let's start our simple queue and test out our new dequeue functionality. Asynchronous functions. Asynchronous requests are handled with the handle cast callback. Handle cast. It's a strange. This works. This works much like handle call 3, but it does not receive the caller and is not expected to reply. We'll implement our enqueue functionality to be asynchronous, updating the queue but not blocking our current execution. Let's put our new functionality to use. Cast, spell cast, magic cast, wizardry. OTP Supervisors. Supervisors are specialized processes with one purpose. You have one job, monitoring other processes. These supervisors enable us to create fault-tolerant applications by automatically restarting child processes when they fail. Configuration. The magic of supervisors is in the supervisor start link function. Yeah, I've seen this in Phoenix. Don't really know what it does. In addition to starting our supervisor and children, it allows us to define the strategy our supervisor uses for managing child processes. Using the simple queue from the OTP concurrency lesson, let's get started. Create a new project using mix new simple queue -- sub to create a new project with a supervisor tree. The code name for simple queue module should go in lib simple queue, And the supervisor code we'll be adding will go in lib simpleq/application. Children are defined using a list, either a list of module names or a list of tuples if you want to include configuration options. If we run IEX smix, we'll see our simple queue is automatically started. If our simple queue process were to crash or be terminated, our supervisor would automatically restart it as if nothing had happened. Strategies. There are currently 3 different supervision strategies available to supervisors. 1 for 1, only restart the failed child process. 1 for all, restart all child processes in the event of a failure. Rest for 1, restart the failed process and any process started after it. Child specification. After the supervisor has started, it must know how to start, stop, restart its children. Each child module should have a child spec1 function to define these behaviors. The use genserver, use supervisor, and use agent macros automatically define this method for us. SimpleQ has use genserver, so we do not need to modify the module. But if you need to define it yourself, child spec should return a map of options. ID, required key. Used by the supervisor to identify the child specification. Start, required key. The module function arguments to call when started by the supervisor. Shutdown, optional key. Defines child's behavior during shutdown. Options are brutal kill, child is stopped immediately, any positive integer, time in milliseconds, supervisor will wait before killing child process. If the process is a worker type, this defaults to 5,000 in milliseconds, 5 seconds. Infinity. Supervisor will wait indefinitely before killing child process. Default for supervisor process type. Not recommended for worker type. Restart. Optional key. There are several approaches for handling child process crashes. Permanent. Child is always restarted, default for all processes. Temporary. Child process is never restarted. Transient. Child process is restarted only if it terminates abnormally. Type. Optional key. Processes can be either worker or supervisor. Defaults to worker. Dynamic supervisor. Supervisors normally start with a list of children to start when the app starts. However, sometimes the supervised children will not be known when our app starts up. For example, we may have a web app that starts a new process to handle a user connecting to our site. For these cases, we want a supervisor where the children can be started on demand. The dynamic supervisor is used to handle this case. Since we will not specify children, we only need to define the runtime options for the supervisor. The dynamic supervisor only supports the 1-for-1 supervision strategy. Then, to start a new simple queue dynamically, we'll use start child 2, which takes a supervisor and the child specification. Again, SimpleQ uses use genserver, so the child specification is already defined. Task supervisor. Tasks have their own specialized supervisor, the task supervisor. Designed for dynamically created tasks, the supervisor uses dynamic supervisor under the hood. Setup. Including the task supervisor is no different than any other supervisors. Children. Restart transient. Okay. Start link. The major difference between supervisor and task supervisor is the default restart strategy, which is default restart strategy temporary. Tasks would never be restarted. With the supervised tasks, with the supervisor started, we can use the start child function to create a supervised task. If our task crashes prematurely, it will be restarted for us. This can be particularly useful when working with incoming connections or processing background work. Stand up. Oh, snap. OTP distribution. Introduction to distribution. We can run our Elixir app on a set of different nodes distributed across a host or across multiple hosts. Elixir allows us to communicate across these nodes via a few different mechanisms, which we'll outline in this lesson. I'll be back in a little while. I'm going to go exercise and things. Have a good day.